Good afternoon, everyone. Welcome back. Thank you for joining us. I'm Steve.
And I'm Scott.
Together, we are Backyard Musing, Science and Technology, Apple Valley.
Yep, and we're talking about a pretty interesting topic today, a little space oriented and definitely
Physics.
science.
Yeah. Astrophysicists at the University of Chicago have developed physics-based models suggesting that dark energy could be changing over time. Dark energy, a mysterious force causing the universe to expand at an accelerating rate, remains one of the biggest puzzles in modern cosmology. What does that have to do with beauty? Doing your hair and face and stuff.
Cosmetology.
Oh, this is cosmology. Okay.
Right.
All right. The leading theory today holds that dark energy is a constant property of space itself, with the vacuum's intrinsic energy driving cosmic acceleration. These findings were published in the Physical Review D on September 8th, 2025. Would you like to know more?
Okay, so as usual, most of these space related topics, I have no idea what we're talking about, and this is no different. So Here we go. Yet, new results from the Dark Energy Survey and the Dark Energy Spectroscopic Instrument released last year have sparked renewed debate by suggesting that dark energy may not be constant at all, but instead evolving over time. Quote, this would be our first indication that dark energy is not the cosmological constant introduced by Einstein over 100 years ago, but a new dynamical phenomenon, explained Josh Freeman, professor emeritus of astronomy and astrophysics.
Yeah.
Doesn't say where he's at, so I'm going to assume he's probably at the University of Chicago.
Yeah. Okay. And kind of correcting Einstein, that's got to be big. By combining data from multiple observational probes, the researchers found that models describing dark energy as a dynamic, evolving quantity align more closely with current observations than those assuming a fixed cosmological constant.
What you were saying about that's almost like messing with Mother Nature, right? You don't mess with Einstein, so.
Right.
Okay, I'm not. This must be a guy, a person. Shajib's research focuses on observational cosmology and galaxy evolution using strong gravitational lensing to measure the Hubble constant and place constraints on dark energy's properties. Fryman's work centers on large-scale cosmic surveys, including the Sloan Digital Sky Survey, SDSS, and DES, which with the goal of uncovering how the universe originated and evolved. Okay, here we go. And ultimately, what dark energy truly is. We spoke with Hajib and Fryman about the new models presented, not we did, but they did in this article, and in their study, and what these findings could mean for cosmology and what future research might reveal.
Yeah, so this is a back and forth between Freeman and Shajib. Okay. So here's Freeman. We now know precisely how much dark energy there is in the universe. Wow, okay. But we have no physical understanding of what it is. The simplest hypothesis is that it is the energy of empty space itself, in which case it would be unchanging in time, a notion that goes back to Einstein, Lemaitre, de Sitter, and others in the early part of the last century. It's a bit embarrassing that we have little to no clue what 70% of the universe is. And whatever it is, it will determine the future evolution of the universe.
Okay, and this is Shajib's point of view. Although there have been interest in the dynamical nature of dark energy since its discovery in the 90s to resolve some observational discrepancies, until recently, most of the major and robust data sets were consistent with a non-evolving dark energy model, which is accepted as the standard cosmology. However, interest in evolving dark energy was vigorously rekindled last year from the combination of supernova, right? Supernova?
Supernovae. So that's
Nuvae. It's a plural.
Okay. Yeah.
Baryon acoustic oscillation and cosmic microwave background data from the DES, DESI, and Planck experiments.
This combination of data sets indicated a strong discrepancy with the standard non-evolving model of dark energy. The interesting feature of non-evolving dark energy is that its density stays constant through time, even though space is expanding. However, for the evolving dark energy model, dark energy density will change with time.
Okay, so now we're going to go back to the back and forth, and this time I'm talking about Feynman's point. The data from these surveys will allow us to infer the history of cosmic expansion, how fast the universe has been expanding at different epochs in the past. If dark energy evolves in time, that history will be different than if dark energy is constant. The cosmic expansion history results suggest that over the last several billion years or so, the density of dark energy has decreased by over 10%. Not much, and not much less than the densities of other matter and energy, but still significant.
Billions of years, yeah. Shajib and Freeman says the goal of this study is to compare the predictions of a physical model for evolving dark energy with the latest data sets and to infer the physical properties of dark energy from this comparison. The evolving dark energy model used in most previous data analysis is just a mathematical formula that isn't constrained to behave as physical models do.
In our paper, we directly compare physics-based models for evolving dark energy to the data and find that these models describe the current data better than the standard non-evolving dark energy model. We also show that near future surveys such as DESI and the Vera Rubin Observatory Legacy Survey of Space and Time will be able to definitively tell us whether these models are correct or if instead dark energy really is constant.
So Freeman says these models are based on particle physics theories of hypothetical particles called axions. Axions were first predicted by physicists in the 1970s who sought to explain certain observed features of strong interactions. Today, axions are considered plausible candidates for dark matter, and experiments worldwide are actively searching for them, including physicists at Fermilab and the University of Chicago.
The models in our paper are based on a different ultralight version of the axion that would act as dark energy, not dark matter. In these models, dark energy would, in fact, be constant for the first several billion years of cosmic history, but the axion would then start to evolve, like a ball on a sloping field that's released from rest and starts to roll. And its density would slowly decrease, which is what the data appear to prefer. So the data suggests the existence of a new particle in nature that's about 38 orders of magnitude lighter than the electron.
Gee whiz, that is pretty light.
Okay.
So Shajib says in these models, the dark energy density decreases with time. Dark energy is the reason for the universe's accelerated expansion. So if its density decreases, the acceleration will also decrease with time. If we consider the very far future of the universe, different characteristics of dark energy can lead to different outcomes.
And this is Freeman's last hurrah here. The only particle implications I can imagine are the technologies we need to develop to explore these ideas further, building new telescopes, launching new satellites, or developing novel detectors, for example. Such developments are likely to have more of an impact on our lives than events happening trillions of years in the future. So,
yeah, of course.
I mean, this is a niche right here. These guys that are exploring this stuff, I guess, because I don't see a whole lot of people just running up and giving them a bunch of money, but maybe so.
You heard it first here, right?
So, yep.
All right, folks. Thanks for joining us. We'll catch you tomorrow.
Take care, everyone. Have a great night. Thanks.